All right, is that mic on? Yeah, good. All right, here we go then. Sorry about the Panopto thing on Friday. I think that's the second time this semester that happened. It's just random events. It just shuts off and it gives no warning and no... Anyway, so somebody posted it on Piazza. I got some email from some of you. I went ahead and re-recorded the last part of the lecture yesterday. It was a little rushed, but at least you have it, and so you can watch it. How many of you are done with homework 3? Anybody done? A few of you? Almost? Okay, we still have till Friday. I'm extending the usual 24-hour late period until Monday evening at midnight, so you have 3 days of late time if you need it. Remember how that works. You get full credit for what you did up to 75% of the credit of the problem. So it's not like you get 75% of the points you earn. You get all the points you earn, but you can't exceed 75% of the grade. There are a lot of questions on Piazza. I realize you can't see all of them because some of them are private, but please read the ones that aren't private before you ask your questions, so we reduce the number of duplications. TAs are still grading homework 2. It may take the rest of the week. They're not moving as quickly as we would like, but that's also because they have their own work to do and their own classes, and it's final project time. So we'll get it done this week. And we'll post those final grade estimates that people have been asking about. I think it's better to wait until homework 2 is graded to post them so to be more complete. If you want me to post them before, I can do that, but then I won't post them twice, so you'll have to tell me what you prefer. And it's not like the knowledge will change your behavior, right? You still have homework 3 to do, and you still have to study for the exam. So I think the later it is, the better before the exam is what we're hoping for. What we'll have. And the exam is here, Friday, May 13th from 3 to 5 p.m. Those with SDS accommodations, including people who've just sent me those, I'll communicate with you, but we'll handle it the same way we've always handled it before, which means you'll take it in the proctoring center for extended time. Okay, I posted this the other day. These are all the materials that we covered. Most of these chapters are assigned readings, not quite all of them, but they all cover, all the material we cover was covered in those chapters. A good place to start if you're reviewing for the exam is to skim through those parts of the textbook. All right, so we have 3 lectures left. I understand I have to give you some time in the lecture to consider doing the ACE form evaluations, or whatever they call them now, spot forms, ACE forms, student evaluation forms. So I asked myself, what could I do in a few class periods? And what I want to do is I want to talk a little bit about theory of computation, not in a deep way, but I'm going to go back and do the stable marriage problem again. We're going to implement it. We're going to talk about its runtime in the way we now know how to do with analysis of algorithms. We can talk about runtime in a meaningful way. And then we're going to spend some time talking about termination. And I want to introduce a problem called the halting problem. Anybody heard of the halting problem before? Anybody? One of you? Okay, so the halting problem is this kind of neat construct that there's a proof that goes along with it that shows that you cannot prove that a program will terminate in the general sense. So there is no proof that a given program will terminate. It's not like I can write a program that looks at your code and says, oh yeah, this will terminate. Can't be done. And I want to show you that proof not because it's such an important proof, I mean it is important, but mostly because it's an example of the kind of sort of philosophical foundations that people explore in theory of computation. Most people think of computer science as being, well, either about video games or about programming or whatever, but it really is about problem solving and algorithms, and it also has this really cool philosophical part to it. All right, computer science is much broader than you might think, and I think it might be fun just to get a taste of some of the philosophy that goes with computer science. So we all remember this. This is the problem we did first day in class. Stable marriage problem. We had n men and n women. We wanted to come up with a set of matching, or a matching, which is a set of pairings, 1 man, 1 woman pairings, such that there are no 2 matches that would be better off exchanged. So in other words, there's no, given that every participant has a preference for who they want to be matched with, there's no reversal of match that would improve the pairing for everybody. And we did this little exercise, and this was the solution we had in mind. So let's review this solution for a second. We're going to choose a man at random, and we're going to have him propose to his first choice. So everybody has rank ordered all the other participants. So every man has a list of women in preference order, and every woman has a list of men in preference order. And those lists are complete. They rank everybody. So what we're going to do is we're going to pick a man at random to be the suitor, and he's going to propose to his first choice partner. And the partner, who is not engaged because we're just starting the match, will become engaged to this person. And then we'll just pick another man from the pool randomly. He'll propose to his first choice partner. And eventually you're going to get you're going to be done because everybody will propose to their first choice partner and there's no contention, so everybody gets their first choice. Or we come up with a situation where a man proposes to a woman who's already engaged. And at this point, the woman has to decide whether she prefers the new suitor to her current fiancé. If she prefers the suitor, she has to dump the fiancé, basically rejecting him, and accept the engagement, the proposal from the suitor. But if she prefers her current fiancé, she just rejects the suitor outright. And we keep doing this as long as there are unmatched men in the pool, because when a man is dumped, he goes back into the pool of unmatched and can be chosen again at random. Now, I realize this is horribly gender-specific language. I, at one point, sat down and rewrote this with suitors and type 1 and type 2, and it just becomes confusing for me to keep it straight too, but also it just becomes more archaic. The use of man and woman here does not imply any gender. You can switch woman and man. You can have woman propose first. In fact, this is a completely symmetric problem. It's just easier to talk about it this way. I also experimented with ducks and geese, but then it just came out weird. It's just not. So anyway, so here's our runtime example of one run of the algorithm. James has picked at random first, proposes to Maria, who is his first choice. Maria is not engaged, so she accepts the proposal. James is unfortunately her last choice, but now they're engaged, and so we have one part of our pairing done. Our next suitor is Roger, who proposes to Mimi, who again is not engaged, so she accepts the proposal, and we get the second match. At this point, when Mimi accepts the proposal from Roger, there is implicit in the sort of description of the algorithm we gave the fact that her next acceptance, her next engagement, will always be with somebody who moves her up her list. So Mimi's choices will only get better. And it's another way of saying nicely that once she gets engaged to Roger, she never has to consider a proposal from Tony because she has a dominating choice already in hand. In contrast, the men's proposals, they start higher, but as they get rejected or dumped, they'll move down their list. And so we have one set going down and one set going up. And that's important to understand for the termination argument we'll make later. So next we'll pick Tony, and now we have our first contentious proposal. He proposes to Maria. Maria's already engaged to James. Now she compares Tony and James on her list. And in the sense of what I just said, we're going to make an improving choice. So she's going to cut James loose, scratch James and Wesley off her list, and accept the proposal from Tony. Now at this point, James goes back in the pool, and we know that James will never be able to be engaged to Maria because she's already dumped him. That means because she dumped him, it means she already has a fiancé who she prefers to James, and there's no reason for him to continue asking because in this world, your choices are made at the beginning and don't change. So we'll pick another man from the pool. We pick Wesley. He proposes to Buttercup. She gets engaged because she has no other fiance. And again, she can cross off anybody lower than Wesley because as the match evolves, her choices will only improve. Whereas for men, as the match evolves, their choices will only go down. Nick proposes to Mimi. Mimi accepts the proposal. She crosses James and Roger off her list. Roger goes back to the pool. We pick Roger again from the pool. He gets a second chance. He proposes to Buttercup, who is his second choice because Mimi's already rejected him. Buttercup prefers Roger to Wesley, so she cuts Wesley loose and gets engaged with Roger. Now we still have Wesley and James in the pool. We randomly pick Wesley. He proposes to his second choice, Nora. Nora accepts his proposal because she's not engaged. And then finally we pick James again from the pool. He proposes to Buttercup, who is the second choice, but she has her first choice already. She's not going to go back down the list, so she rejects him. He proposes to Nora, who's his number 3, and Nora compares his list. He's her last choice. She's already got a number 3 choice, so she rejects him. And he proposes to Lily, who's not engaged to anybody, and she accepts. So we talked a bit about this in the very first day of class, about how the algorithm was specified with this kind of nice sort of, you either dump, you propose, you engage. There was this sort of nice language we could use, given to us by the wording of the problem. And we talked about termination, the fact that at some point, everybody's going to match somebody because everybody has ranked every other person in some preference order. And as long as you keep proposing, James went down the list quite a bit, but at some point he will find somebody on this list who is not engaged and will accept his proposal. And we know that because there's an equal number of men to women, and women can only be engaged to one person at a time. And so eventually he's going to be okay. He'll get somebody. As for the woman, the analogous symmetric argument holds. They may not get picked right away. Lily was the last one chosen, but eventually somebody will ask her because eventually somebody will have to go down their list and she'll be their choice. Or eventually the last person picked from the pool will randomly, at random will be the one that picks her. So, does everybody understand the algorithm now? Does it seem easier now than the beginning of the term? Straightforward? Okay, so it's described completely. It's not a recipe. It doesn't say do this, do that, then do the other. It tells you, however, everything that you need to do at every step of the algorithm. So in a sense, it's not, when you start a CS class, I always tell you, a program is like a recipe. It tells you how to do things in order. It doesn't have to be that way. In fact, this is really a protocol. When we say the word protocol, we mean a set of rules that tell us how to behave, essentially. You've probably heard the word protocol when talking about network protocols. You know that HTTP is a hypertext transfer protocol. It tells both the client and the server how they should interact with each other, what to respond when asked appropriate things, and how to reject something that's not appropriate or is out of sequence. So these are protocols, and I gave you a protocol for the stable marriage problem. And from that protocol, we derive a solution, an implementation, or an algorithm. There's a lot of work in computer science at the intersection between computer science and, of all things, game theory. Has anybody had a game theory class? I don't even know if there is one that's not a graduate course. So in game theory, we talk about, whether games are, for example, zero-sum. A zero-sum game is one where both players have equal probability of winning the game, that there's no advantage in moving first. And the second implication of a zero-sum game is that every time I gain an advantage over you, some quantifiable advantage, then you have the same quantifiable disadvantage with respect to me. So a zero-sum game means at the beginning of the game, it's like, well, chess isn't quite zero-sum, but it's like a game where you sit down to play, and if your opponent offers you a draw at the very first move, you should accept it because that's your best, safest bet. You always just tie. Right? That's what it means to be zero-sum. By playing the game, you can only lose as your opponent gets better, or you can win if your opponent makes a mistake. It's at the expense of your opponent. So we know here it terminates because we have this sort of pigeonhole argument about the number of people and the number of proposals they can make. But what we really haven't talked about much is the runtime of the algorithm. So let's talk about the runtime. Remember that when we talked about algorithmic analysis, we talked about how runtime was a worst case kind of reasoning thing, back of the envelope worst case. So here in the worst case, what will happen is that every man will propose to every other woman, right? We saw James had a pretty rough time of it. He started with one proposal, he got dumped, and he got dumped again, he proposed, he was rejected, he ended up on choice number 4. The worst possible case is that every man proposes and eventually gets dumped by n minus one woman and proposes to the last one who then accepts him. So, in a sense, the worst case of this algorithm is going to be order what? So if you have n men and n women, and every man proposes to every woman, and if we accept that the proposal is the sort of fundamental unit of computation is the proposal, there will be at most n squared proposals in the worst case. We also argue about the correctness of the match, that there's no partner swap that improves the outcome. Why? Because as a man goes down his list, he never skips a woman on his list. So he always goes down the list one at a time. If there were a partner swap that improved the man's outcome, then that means there's a woman that he prefers to the one he's currently matched to, who at some point he must not have proposed to. Right? Because if he had proposed to her, she would have accepted. She would have had to accept. Because she's also matched to somebody who is less desirable than the man that we're talking about. So by construction, we know that there is no improving swap. And again, you can run the algorithm. The gender doesn't really matter. You run with women proposing to men. So let's implement it. So I sat down and wrote the code for this, and I did it in an object-oriented way because why not? Now, I'm not a big object-oriented fan, but I saw how you struggled on the last exam, so I figured let's just do this with objects because that's what you've got to get used to seeing. So here's my code. The idea is that I'm going to read in from a file everybody's preference list. So the configuration for this problem is all given by a text file, which consists of 2n lines. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines. That means that n here is 5, where you have first one type of agent. In this case, it's all the men, Nick, James, Wesley, Tony, Roger, followed by all of the other type of agents. In this case, it's Nora, Lily, Buttercup, Maria, and Mimi. So this is actually the preference list for the file I showed you. And in each line, you have an agent of type 1, followed by their preference ordering of all the agents of type 2. So we can see here, Mimi, Buttercup, Nora, Lily, and Maria are all Mimi, Buttercup, Nora, Lily, and Maria are all the other type of agents following Nick. And if I just look at Tony and Nick, we see that all the names that Tony has ranked are the names that Nick has ranked. We do the same thing with the woman, and we see all the men are ranked there. So we would like our code, I apologize for the page break, we would like our code to allow for either side to do the proposing. When we did this the very first day in class, I explained to you that the end result wasn't quite symmetric. And I showed you that the proposing side had a little bit of an advantage. They tended to end up with higher ranked choices than the passive sides that waited for the proposal. They tended to end up with slightly lower ranked choices. Now, it's not guaranteed. It's order dependent, and it has to do with how the preferences are structured. But in general, that's sort of the case. And I think I also told you that the National Residency Matching Program was changed in the summer of 72 or something, or 71, or some weird time. I forget, it was in the 70s, as a result of a lawsuit, because the hospitals were playing the part of the men and seemed to have better results than the residents who were playing the part of the women. So they reversed the way proposing worked to give the residents a better geographic choice. So we would like our code to be agnostic as to gender and work either way. Let the women propose, let the men propose, and so on. So the specification of our algorithm that we talked about briefly with the proposing and dumping and so on suggests several methods in the design of our object. We're going to have one object called stable marriage object, and it's going to represent a problem, a stable marriage problem, and you'll be able to run a method of stable marriage to get a solution. You'll be able to do it again to get a different solution. So you'll be able to call it differently every time you want, as many times as you want. So the first method is a read prefs method. This takes the agent preferences. Actually, there's an argument missing here, which is the preference list, the name of the file. We have an engagement method, which establishes that M and W are engaged to each other in some internal representation. We have a dump method that ensures that W, the current W, dumps whoever she is currently engaged to. So whatever match she has is terminated. And we have a propose method that says M is proposing to W. Now again, M and W, there's no gender here. In fact, when we run it inverted, the M will actually be a woman's name and W will actually be a man's name, but it's just a way for us to keep them straight. And there's several data structures. First of all, we have a list of names, N, which contains the men and women's names from the preference file. We have a dictionary of preference list indexed by name. So if I look at self.d for the value Nick, I will get back a list of women's names in preference order. And I have a dictionary, M, which is a dictionary of matches. So here is where I have, you know, the key Nick associated with the value Mimi, and at the same time I have the key Mimi associated with the value Nick. So these are maintained in a symmetric fashion. So when you get engaged, we make two entries into the dictionary, man pointing to woman and woman pointing to man. And finally, we're going to have a list that starts out with all of the men or all of the women, depending how you're running things, which is our list of unmatched suitors. And that's the list that we're going to choose randomly from and for the next proposal. So we're going to manipulate that list. Starts out with all the men, say. I'm going to pick one at random and pop them off the list. I'm going to let them propose, and I'm going to keep doing this. And if somebody gets dumped, they go back in that list where they can be recycled. And again, we want it to work with the roles reversed as well. So here's my class, sort of what you would expect. You'll see the argument that I had missing on the previous slide is here. So I'm going to call my class stable marriage. There's an initialization method, and the point of the initialization method is to read in the preferences file and set up the structure of the problem. So these are the variables we just talked about. The initialization method, which is the constructor to stable marriage, takes a file name as its preferences, a flag that tells you whether you want to invert gender, so men propose versus women propose, and another flag called debug, which is a Boolean, true or false, which governs how much, how verbose the output is when I run the match. So I mean, there's other names for this kind of thing. It's a pretty common thing to have like a verbosity level. This might be verbose, true or false. Sometimes these, instead of being Booleans, actually have integers. So 0 turns it off, 1 gives you a little bit of output, 2 gives you more output, 3 gives you even more output. This is really good coding practice to have some amount of output as your code runs that can be regulated at runtime and defaults to having no output. So this is something that's commonly done. And we see in the method, we just basically set these up to be a list of names and 2 dictionaries. The debug input is just made a flag, an instance variable here. We invoke the read prefs method, passing the name of the file here. So these are all read in and presumably are set up in the preferences and names. And then we call self.run, which is the method that runs the match. And we pass it the inversion flag to tell it whether we want it to run with men proposing or with women proposing, depending on the flag. Okay, so the preference file lists the men agents preferences first, and this women's agents preferences second, and they have to balance. So in other words, if there's 5 men, there have to be 5 women. Each one has to have a list of 5 preferences. So here's how I read this in. This should be pretty straightforward, or appear pretty straightforward to you. We pass in the name of the file that we specified when we created the object. That opens the preferences file for read as in file. This is the hot file handle. And we're going to do a read here, line by line read. And what we do is we read in the line, we split the line to get a list of names, individual names. If you recall what the preference list looked like, the first name was Nick, and then he had Mimi, Buttercup, and so on. So the first name in this names list will be the agent type 1 name, and the remaining names will be the ordered type 2 names. And what I do here is I take the first name, name 0, which is the first agent type, and I append it to the list of names that I keep in my object, and then I set up the dictionary of preferences. This is the preference listing for name 0, which is like Nick, and then these are all the remaining names, the list of remaining names that were his preferences. So this basically sets up the problem. And you have to notice that names in self.n are in the same, they're appended, so they end up in self.n in the same order as the lines in the input files. If I have all the men first and all the women next, it'll be all the men first and listed and all the women. If I instead had all the women first and all the men, then it would be all the women and all the men. Doesn't matter. But they must be all of one type first, followed by the other type. No mixing of types. Okay? So name order determines the agent type. And the other thing you'll notice is, and this is probably bad form, there's no validation of the input. I could validate this input, and if I were doing this carefully, I probably should. And by input validation here, it's always good to stop when you write code that reads something from a configuration file, from a user input, to ask yourself, what can go wrong? Because this will save you trouble down the line when something goes wrong and you're not really sure where the error originated. So if you were really to write a bulletproof preference reading file, what I would have to check is I would have to ascertain that every name key in self.d has an appropriate list of names in terms of length, right? It has to be n elements. And that all the names in every element D's list are names of the opposite type as the key. And I would have to check that that the self.n is even numbered, and that, you know, using the first half as one type and the second half as another type works, and that all the preferences are respected. It's not hard to check that. You can imagine how you might do it. You would take these the values here and turn them into sets. You'd make sure that all the sets in the first half were the same and all the sets in the second half were the same, and that those sets were disjoint, so men and women and so on and so forth. So you could do this pretty simply. I didn't bother. That's probably not what I should have done. I probably should have bothered. Questions? So assuming I have a stable marriage object S, I can look at its list of names. Oops, here I ran overboard, but there's Nick, James, Wesley, Tony, Roger, then Nora, Lily, Buttercup, and I guess Mimi, and somebody else is missing, Maria or something. And I could, yeah, Maria, in fact. If I look at the dictionary entry for Nick, I see that there's a list of his preferences. And likewise, if I look at the dictionary reference of all of them, I will see that I have Nick, James, Wesley, Tony, Roger, and their lists are all lists of the other type of agents. So these are the sets I want to make sure are all the same. I'll make sure these sets are all the same, and that this set is the same as this set, and that these sets are the same as this set. And if I did that, it would be a couple of set operations, and I could easily detect errors in your preference file and give you a diagnostic and quit, which is what I should do. Questions? All right, so we had 4 methods. Aside from reading the preferences, we had a run method which managed the match, and we're going to do that first. And then we had 3 other methods that corresponded to getting engaged, to dumping your fiance, and to proposing. And we're going to see those methods one after the other. They're just basically going to follow the specification we gave in text. So here's the first one. There's an inversion flag here, and you see how it's handled here. We set up the suitors list based on the inversion flag. If this inverters flag is true, then the suitors will simply be the second half of my name list. It will simply be the, is this the second half? I have these backwards, don't I? Yep. So this is the second half proposes to the first half. The comments are inverted. And here, if inversion is false, then we have the first half proposes to the second half. I apologize, those 2 comments are backwards. So remember, the names as we read them in were in the same order as in our preferences file, which had men preferences first. So if inversion is true, then we're going to make suitors out of the second half, which are the woman. And if inversion is false, which was the default, we're going to make suitors out of the first half, which were the men. So that's all just setting up the suitors list. And then there's just a big loop here. And the loop says, well, I've got somebody left who's unmatched. I'm going to choose a suitor at random. So you'll notice here the use of pop and the random integer together. This is a very common idiom. If you're given a list and you're asked to choose an element of that list at random without replacement, right? In other words, you want to consume an element of the list when you choose it. This is the way to go. The pop method of lists takes an index, removes the element located in the list at that index, while at the same time returning it as a value. So pop is a little bit like a deletion and a return combined together. It's like setting a variable and saying, remember this element I'm about to get rid of. Pop the element, throw it away, and return the thing that you remembered. And this is all done in one fell swoop with pop. It takes an index into this list. Well, the list goes from 0 to length of self.suitors minus 1. Remember, randint violates the usual Python indexing scheme and is inclusive on both ends of the range. So this gives us all of, range that corresponds to all of the elements in the suitors list. I'm going to pick one at random. I'm going to remove it and return it as a value s. And now we see the little debug flag. It says, if self.debug is true, then I'm going to print out this little informative message that says that so-and-so, which is the name of the person I just popped off the list, steps up to the plate. And then we're going to get that person walk down their list, proposing along the way. So S will propose to the very first person in their preference list. And if it returns false, meaning that the proposal is rejected, so while this is false, we're going to print out a message that says, sorry, Charlie, Mary said no. And what we do is we shorten the list by removing that first element, crossing out the person who just rejected you. Never go back to them. And you keep doing this over and over and over again until you get a proposal that sticks. Now, notice that I don't worry about D being completely empty. I don't worry about it because I know theoretically that if the preferences are done correctly, and again, I should have checked the validity of the preferences, this will never become empty. There will always be a match for everybody. So I don't need to check that condition. I can do this with confidence. And at the end of the day, if the proposal works out, we have to see what happens to our internal data structures. I assume that if the proposal works out, those two people will become engaged and they'll show up in the marriage list and the match list. At the end of the day, when there are no suitors left and everybody is matched, I just return the match and I'm done. Any questions here? So, better code than what I've written for this class would have some elements in this that I've not described, or I've not described in the comments. There will be a comment here that says, no need to worry about running out of choices because we've proven theoretically that everybody's choice will eventually match to a choice. And that would be a comment presumably right here in the code or up here up front at the beginning of the code. And maybe an element here in saying, read prefs, make sure that this condition is maintained when solving the problem. Okay? So let's take a look at the next method, which is the proposal method. This is when M proposes to W, and we either have to return true if the match is made, or false so that the suitor can be rejected and he can go on and propose to somebody else. So here's the proposal method, very straightforward. There's a message here that says so-and-so proposes to so-and-so, and then we do a little bit of checking. So if W is already matched, if they already have a fiance, and M, who's the proposer, is in W's choice set, Now remember, we've seen in the suitor picking, as the suitor goes down their list proposing, that we actually manipulate that dictionary of preferences, right? When somebody's rejected, we remove that choice from their preferences. I'm going to tell you here that I do the same thing for the woman. When the woman moves up in the list, when she gets engaged, she's going to delete the less preferred men from her list. So if the woman is already engaged, she's in the match, but the man who's proposing is still in her choice list, that tells you that, yes, she's engaged, but she prefers the new suitor to the old one, because only thing left on her list are improving choices. And so this suitor represents an improvement. So she has to do a couple of things. The first thing she has to do is she's got to dump her current choice. So whoever she is engaged in, we're going to call the dump method and get rid of him. All right, we'll see that in a minute. That's the only thing we really need to do, because it falls through to become a match. We can execute the engage method that presumably manipulates the marriage list and then return true because we were successful. On the other hand, if the woman is in the match, but the man that's proposing is not still in her preference list, that means that she prefers the current fiancé, and she can just reject this proposal and return false. And so that's what she does. So the proposal method, this may not be the best control structure you've ever seen, but it mimics exactly what was given in the specification. So if you read the specification again, you'd say if she prefers this person, then she should get engaged to him and dump the other guy, and if she doesn't, she should just reject them. And this matches word for, in order, the specification we were given. All right, so when you manage to get a match, you have to get engaged, and we point out that the engagement is symmetric. So let's take a look at the engagement method. M and W are going to get engaged. We print out some helpful information. We set man's marriage to woman and woman's marriage to man. And if, and in this case, what I want to do is I want to manipulate both the man's choice list and the woman's choice list to remove the current person. In the case of the man's choice list, I'm going to remove the current woman from his preference list, because if he were ever to get rejected by her, he can't propose to her again. She's going to reject him, so we may as well shorten the list and get rid of her. So we're going to just pop the first element off this list, which is the woman he just got engaged to. For the woman, it's a little bit different. We're going to find out where the current engaged man is in her list, and we're going to set, starting from that man onto the end of the list, we're just going to get rid of him. So we're going to delete from her preference list her current fiancé and everybody who comes after him. So men's lists get shortened one at a time as they propose. Women's lists get shortened by whole chunks at a time as they make these sort of leaps of better and better matches. And dump is sort of what you'd expect it to be. The woman dumps the man, so what she's going to do is we're going to append the man back to the suitors list, right? So the suitors list, and then we're going to pop the woman's match from the match, right? So we're going to pop from the dictionary the key woman and the man, and that will return the woman key, which will pop from the man the man key, the value, which will pop from the match as well. So this double pop removes both sides of the match. Well, that's pretty much it. So let's review the runtime of this algorithm, and then we can start talking about more philosophical questions. So we're going to identify the proposal as the element of work. It's the thing that seems like the basic sort of thing that happens in this algorithm, that we know the number of proposals vary with the input size, so it seems like a reasonable measure of work. In our previous analysis and sorting, we looked at the number of comparisons as the basic element of work. Here are the number of proposals, the basic element of work. Minimum number of n, the best you can hope for is that every man proposes to his first choice and every woman accepts. And if you get that, then the choices are not contentious. It'll only take n proposals. and the worst case is n squared. Now, we talked about this just a minute ago, but it's not clear to me, and it should not be clear to you, that we can construct a preference ordering where the worst case behavior is always experienced. So remember when we did quicksort, we relied on non-determinism to actually improve the performance of our algorithm. Remember this? When by using random pivoting, we avoided the case where if the list was almost sorted, we would get the very bad runtime behavior? Yes? No? Remember that? Okay. So we're doing the same thing here. By randomly choosing suitors, it makes it very hard to construct preference orderings for my n man and my n woman that always give me the worst behavior. Right? It's hard because I would have to have some control over the order in which men ask or propose. So we can't construct this example that could be reached reliably. We may be able to reach it once, but not for every case. So the pseudo order is randomized, and it's actually possible, I believe, although I haven't done it, to argue formally that there's no set of preference that produces the worst case behavior for every order of suitor request, for every random order of suitors. But it's easy enough to come up with an ordering where for a specific order of suitors, you get the worst case behavior. So we know in the worst case it's order n squared. We just don't think it happens very often. This is entirely analogous to quicksort with random pivoting. We know there's a worst case behavior, but you'd have to be really, really unlucky to get it. You'd have to randomly choose the wrong thing every time. And that's sort of the same thing at work here. Is everybody okay with this? Makes sense so far? Okay. So in the worst case, it's order n squared work. In the average case, we can assume that a man will make roughly half as many proposals as he has women on his list. So that means that we're doing n times n over 2 work, but that's still order n squared. So this algorithm appears to be very solidly order n squared, and I think that's certainly the case. Now, thinking back to the first lecture, we said we wanted the algorithm to be efficient, but we also wanted to know that the algorithm would always terminate. And can we prove termination for this algorithm? The answer here is yes. There's a formal argument we can make. Every man ranks every woman, so eventually, and the matching has to be 1-to-1, so eventually we can show that you always end up with a matching. But that's not the case for every problem. And so here we get to the gist of what we're going to cover the rest of this week. So we've just had a little bit of analysis of algorithms, and we've seen some classes of algorithmic problems. We've seen problems that run in less than linear time. Who can name a less than linear time algorithm? Anybody? Yeah, in the back. Binary search or logarithmic time, which is less than linear time. We've seen algorithms that are linear time, like an algorithm that looks for something in a list by scanning. That's a linear time algorithm. We've seen algorithms that are n log n in the average case. That's quicksort with randomized pivot. We've seen algorithms that are order n squared in the worst case, like sorting, and now like matching. So we've seen a bunch of algorithms of different specific runtimes. What we haven't seen are algorithms that are worse than polynomial time. So let's talk about what that means. So an algorithm is intractable when larger versions of the problems take exponentially more time than smaller versions, or worse. So in our sorting example, we know that as the list gets longer, the amount of work we have to do to sort gets slower, it gets quadratically slower. But the n in our order of analysis is still in the base. It's not in the exponent. So in other words, something that's order n squared is bad. Something that's order 2 to the n is really bad. And when we have a problem that is an exponential time problem, we say that problem is intractable. We have a problem that is polynomial time, or doesn't have the n in any exponent anywhere, we say that problem is tractable. Doesn't mean it's always solvable, but it means there are algorithms that are efficiently useful to solve problems of reasonable size. Of course, for any computer, n squared is eventually big enough that you're not going to want to wait for the answer. But 2 to the n gets big enough really, really quickly. And you're not going to want to wait for the answer regardless of how big your supercomputer is when a problem is exponential time. So sorting is a tractable problem. It grows as n squared or n log n, depending on the algorithm you're using. The traveling salesman problem is an example of an intractable problem. Now, we haven't talked about the traveling salesman problem, so I'm just going to introduce it briefly so you know what it is. It's a classic problem in operations research. It starts with a map. Imagine that you are a salesman or saleswoman, and your job involves visiting all of your clients every day. So you go from client to client to client to client. And you start from your home, and you have to drive to each client on the map, and you want to pick what's called a tour, which is starts from home and visits every client and returns to home, such that you minimize the miles you drive. All right? Now, it turns out that if you think of your problem as having n cities that you have to visit or n places that you have to visit, you have n choices for the first one, n minus 1 choices for the second one to visit, n minus 2 choices for the third one to visit, and so on. This is n factorial choices. So you have n factorial different tours that you can make. So when you're saying, okay, I've got to come up with my schedule for today, what order do I visit the cities in? Well, here's all n factorial orders, pick one. Now, a lot of these orders would be stupid. You don't want to have an order that goes to this city, then that city, then back to this one, and back to that one. So some of them you can get rid of. But the fact is, to find the optimal one, and there's only one that is the shortest one, you're going to have to look, in the worst case, at factorially many orderings. And that factorially many is actually, there's a formula that relates it to an exponential expression in n. So something like order 2 to the n. Now, what does that mean? That means that another example of this is gate scheduling for an airport. You have flights arriving at certain times, and you want to schedule them at a gate so that you have shortest paths for passengers to connect. Another example that's strangely, oddly apropos is scheduling final exams, so to minimize scheduling conflicts for students enrolled in the class, which is what we do here. That's also an exponential time algorithm. Finding the optimal solution is intractable. At some point, and this point is very quickly, n will be big enough that you won't be able to do it, regardless of the computer you have to do it. We still solve these problems. They still fly planes at O'Hare, and you still have final exam scheduled. But the solution that's proposed is not necessarily the optimal solution. It is a pretty good solution, but it's not the optimal one. Because if you had to wait for the optimal one, you'd be graduated, you'd probably be dead by the time we got the optimal final solution for everybody in this class. Now, the paradoxical thing here is that for this class of problems that are exponential time, for many of these problems, if I were to give you a solution and say, here's a solution to your traveling salesman problem, you could look at that solution, you could write an algorithm to examine that solution, and tell me that that solution is in fact the best solution. So if I give you the solution, you can verify it. And you can verify that in time that is not exponential. So for this class of problems, for problems in this intractable class, many problems, finding the solution is hard, but checking the solution is easy. And we make use of this really profound philosophical difference in cost when we do cryptographic algorithms. Think about it. If I have an encrypted version of a message, finding the encrypted message, deciphering that, is very, very hard. Unless you have the key, in which case it's very, very easy. The key is the solution, which if I give you the solution to that encryption problem, you can polynomially decrypt the message and read it and say, yeah, that's right. But if I don't give you that solution and ask you to find it, you have no choice but to try all the possible passwords, in the worst case, which is an exponential time endeavor. All right, so this sets up this problem of tractable and intractable problems, which we may touch on later in the week again. But the point of today is that while we have tractable and intractable problems, there's yet another kind of problem called an undecidable problem. So in this class, when we did algorithmic analysis, we really only touched on tractable problems. And today you learned that there are intractable problems that are much, much harder. And more to the point, today you're also going to learn that there's yet another class of problems called undecidable problems that are provably not solvable by machine. Okay? So we're going to pick up next time with undecidable problems, and the example of this problem is called the halting problem, and we're going to show that there is no solution to undecidable problems. Later, if we have time, we'll come back to intractable problems, and we'll talk about how intractable problems are all sort of related to each other in an interesting way. And that interesting way is we don't know if they're truly hard or if we just haven't found out how to make them easy yet. And those are the two big philosophical problems in computer science. Undecidability, which is what we're going to talk about first, and the other one is called whether P, polynomial time, is the same as non-deterministic polynomial time, or NP. And there's $1 million prize out there if you solve the P versus NP problem. So this is something, you're not going to do it next week, but it's intriguing to think about. So this is what I hope to cover for the end of the week. All right, good luck with homework 3, and we'll see you on Wednesday.